Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at Carbon NMR Spectroscopy. We're going to talk about what Carbon NMR Spectroscopy actually is, the theory behind NMR spectroscopy, and how chemical shift data can be used to help analyze organic compounds. The use of Tetramethylsilane, or TMS, as a standard is outlined and specific examples given. Proton NMR spectroscopy and peak splitting have been outlined in separate videos. Check the links in the description below. Before we talk in detail about Carbon NMR spectroscopy, there are a few essential ideas you need to be comfortable with. The nucleus of an atom contains two types of subatomic particle, protons and neutrons. As protons are positively charged and neutrons are neutral, the nucleus of an atom is positively charged overall. Subatomic particles have a property called spin. Spin can be thought of as being a little bit like the direction a particle is rotating in. This isn't strictly speaking true, however, it's a good way of thinking about it at this level. As any object can only rotate in one of two directions, there are two possible directions of spin that a particle can have, represented as positive half and negative half. Isotopes are atoms that have the same number of protons as each other and a different number of neutrons. As they have the same number of protons, they have the same atomic number and are atoms of the same element. However, as they have a different number of neutrons, they have different mass numbers. For example, Carbon-13 is an isotope of carbon that contains 6 protons and 7 neutrons in its nucleus. The most common isotope of carbon, however, Carbon-12, contains 6 protons and 6 neutrons. Recap done? Let's go! Carbon-13 NMR spectroscopy is a technique used to analyze carbon-containing compounds in organic chemistry. It enables the number of unique carbon environments in a molecule to be determined, and information about possible groups bonded to these carbon atoms can be predicted, giving useful clues about the structure of a compound. The N, M, and R stand for nuclear magnetic resonance. Hopefully why those words are used will become a little bit clearer as the video goes on. In a molecule, a carbon environment refers to a carbon atom and the bonds that it has to other groups and atoms. A unique carbon environment is one where a carbon atom is bonded to different atoms or groups compared to other carbon atoms in the same molecule. This can sometimes be tricky to see, as even if two carbon atoms are bonded to the same types of atom, if those atoms themselves are bonded to different atoms or groups, then the two carbon atoms are in different or unique environments. For example, in the molecule ethane, there are 2 carbon atoms, meaning 2 carbon environments. However, there is only one unique carbon environment, as both the carbon atoms are bonded to the exact same atoms and groups, 3 hydrogen atoms and another carbon atom that is bonded to 3 other hydrogen atoms. Whereas in ethanol, there are still 2 carbon atoms, meaning 2 carbon environments. However, each of these carbon atoms are bonded to different atoms and groups. One carbon is bonded to 3 hydrogen atoms and a CH2OH group, and the other carbon is bonded to 2 hydrogen atoms, an OH group, and a CH3 group, meaning there are 2 unique carbon environments in the molecule. Central to Carbon NMR spectroscopy is a naturally occurring isotope of carbon, Carbon-13. When the nucleus of an atom is made up of an odd number of particles, it has an overall spin. This is because the spins of all the particles inside it can't cancel each other out. Carbon-13 is focused on in NMR spectroscopy, as its atoms have 13 subatomic particles in their nucleus, 6 protons and 7 neutrons. As a result, the nucleus of a carbon-13 atom will always have an overall spin of either positive half or negative half. Now, when a charged particle or group of particles spin, they generate a weak magnetic field. If an atom's nucleus has no overall spin, like in carbon-12, then it won't have a magnetic field around it. However, if it does have an overall spin, like for carbon-13 atoms, then it will have a weak magnetic field around it as it spins around its axis, kind of wobbling a little bit in the process. Hopefully you can remember from some of your early physics classes that magnetic fields have a direction based on north and south, meaning a nucleus with an overall spin acts a little bit like a bar magnet, with a very small north and south pole. The magnetic field direction a spinning nucleus has is based on its spin direction. Change the direction of the spin and the direction of the magnetic field around the nucleus also changes, a bit like flipping a bar magnet upside down. This means a nucleus with a spin of positive half will have a magnetic field direction that's opposite to a nucleus with a spin of negative half. If a sample containing carbon-13 atoms is placed in a large external magnetic field, the spin of all the carbon-13 nuclei present will align themselves with this magnetic field and, as a result, become slightly lower in energy and more stable. Essentially, one spin direction becomes lower energy, aligned to the external magnetic field, and the other direction becomes higher energy, against the external magnetic field. The nuclei will all exist in the lowest energy state possible, meaning they all have the same spin with the lowest energy. However, if a specific amount of energy is absorbed by one of the nuclei, its spin can be changed to the higher energy one. If this happens, the nucleus ends up with a magnetic field that is opposite in direction to the larger external magnetic field. This process is called resonance. This specific amount of energy can be given to the nucleus in the form of a radio wave. Only radio waves of a specific frequency can provide the energy needed to flip the spin of the nucleus. Any waves that aren't the specific frequency needed for resonance wouldn't be absorbed by the nucleus and would simply pass through the sample. Here's the really key thing. The nucleus of carbon-13 atoms in different, unique environments to each other absorb slightly different amounts of energy to resonate, and as a result will absorb different frequencies of radio waves. By sending a range of radio wave frequencies through a sample and detecting those that pass through, we can determine which frequencies have been absorbed. The number of different frequencies absorbed will show how many different, unique carbon environments there are in the compound. It is the differences between the frequencies absorbed that are important in carbon NMR spectroscopy, rather than the actual frequencies themselves. Because of this, a standard is used to enable absorptions to be compared for different carbon environments within compounds. The most common standard used is Tetramethylsilane, TMS. In TMS molecules, there is only one unique carbon environment, and all carbon atoms have a relatively high electron density around them. This is because silicon has a lower electronegativity than carbon, meaning each carbon atom doesn't have electron density pulled away from it. This gives a high electron density around the carbon's nucleus and shields it from the external magnetic field used in an NMR machine, making it slightly easier for the spin of the nucleus to be flipped, meaning low energy radio waves of a lower frequency are needed. In all other organic molecules, carbon won't have such a high electron density around it, as it's rare for carbon to be bonded to other atoms with a lower electronegativity than itself. As a result, a carbon nucleus in an organic molecule has less shielding around it, meaning it experiences more of the external magnetic field during NMR, making it slightly harder to flip the spin of the nucleus, meaning higher energy radio waves of a higher frequency are needed compared to the carbon atoms in TMS. How frequencies of absorption for carbon nuclei in samples compare to the frequency absorbed in the standard TMS is shown using something called chemical shift, ppm. The absorption for the resonance of carbon nuclei in TMS is given a ppm of 0, as in everything else is compared to this point. Absorptions that are different and further away from the TMS 0 ppm are considered to be downfield. For example, the carbon atom in methanol is bonded to an oxygen atom. The oxygen has a higher electronegativity than carbon and as a result pulls electron density away from it. This means there is less shielding around the carbon's nucleus in methanol compared to the carbon atoms in TMS. As a result, the nucleus experiences a greater amount of the external magnetic field, and this makes it harder to flip its spin. A higher frequency radio wave is needed compared to the carbon environment in TMS, and this frequency is represented as chemical shift, ppm. By using a graph or spectra, we can easily see how the two absorbances for each carbon environment compare, shown as peaks. Very often, however, the peak at 0 ppm for TMS won't be shown on the spectra, as it's only there as a reference point. The number of peaks in a carbon NMR spectra tells us the number of unique carbon environments in a molecule, and the chemical shift of these peaks gives information about where the environments are compared to each other and how they may be bonded to each other. Even in different molecules, carbon atoms bonded to similar groups have similar chemical shifts, meaning data tables can be produced that enable spectra to be quickly analysed. Like in the one shown, for example, we can see carbon atoms single bonded to just other carbon atoms and hydrogen atoms will have chemical shifts somewhere in the range of 5 to 40 ppm. Carbon atoms double bonded to an oxygen atom in aldehydes and ketones, however, will have shifts somewhere around 190 to 220 ppm. This kind of makes sense based on what we were looking at with electronegativities earlier on. The more electronegative the element of a carbon atom is bonded to, the less electron density it has around its nucleus, giving a greater chemical shift from the carbon reference in TMS. In other words, the further to the left its peak appears on a spectra, downfield of 0 ppm. For example, in propanol, there are 3 different unique carbon environments. In the first, the carbon is bonded to 1 oxygen atom, 2 hydrogen atoms, and 1 other carbon atom. In the second, the carbon is bonded to 2 hydrogen atoms and 2 other carbon atoms, one of which is the CH2OH group and the other a CH3 group. Finally, in the third unique environment, the carbon is bonded to 3 hydrogen atoms and the middle carbon. We can predict where the peaks for each of these carbons are likely to be on a spectra by thinking of the electron density around the nucleus of each. In the first carbon environment, the high electronegativity of the oxygen atom will pull electrons away from the carbon atom, meaning, as we've just seen, a greater ppm shift, far from the 0 ppm reference of the carbon atoms in the TMS standard, around 50 to 90 ppm according to the data table. For the other 2 carbon environments, however, how can we predict which one will be where? Well, the carbon atom in the second environment is bonded to the carbon from the first environment, meaning it will have some of its own electron density pulled away from it and towards this electron-deficient carbon, ending up with slightly less electron density around its nucleus compared to the carbon atom in the third environment. As a result, its chemical shift will be slightly further from 0 ppm than for the carbon nucleus in the third carbon environment. The difference will be small, however it will still be there, giving 2 different peaks, somewhere between 5 and 40 ppm. The chemical shifts for carbons bonded to identical groups will rarely be exactly the same for different molecules, as their exact environment will be slightly different. This means a range of chemical shift values are always given in data tables. So, to summarize, Carbon NMR spectroscopy is a technique used to analyze carbon-containing compounds in organic chemistry. Spectra are produced that can tell us the number of unique carbon environments in a molecule by the number of peaks in the spectra. And also the chemical shifts of these peaks can give useful information about how these environments may be arranged in the molecule. In Carbon NMR, the nucleus of a carbon-13 atom has its weak magnetic field flipped against the direction of an externally applied magnetic field. This flips the spin of the carbon-13 atom's nucleus, and the process is called resonance. Energy is needed to do this and comes from radio waves. Depending on the specific environment of a carbon atom, different amounts of energy are needed to flip the spin of its nucleus, meaning carbon-13 atoms in different environments absorb different frequencies of radio waves as their spin flips. The number of different frequencies of radio waves absorbed by a sample will be the same as the number of different or unique carbon environments in the molecules present. It isn't the specific frequencies absorbed that are important, it's how they compare to each other, meaning a standard is used that all measurements are compared to. A common standard used is Tetramethylsilane, TMS. In TMS, there is only one unique carbon environment, and all carbon atoms have a relatively high electron density around them, due to silicon's lower electronegativity than carbon. This high electron density shields the nucleus from the external magnetic field. In all other organic molecules, carbon won't have such a high electron density around it, as it is rare for carbon to be bonded to other atoms with a lower electronegativity than itself. As a result, a carbon nucleus has less shielding around it, and slightly more energy is needed to flip the spin of the nucleus, meaning higher energy radio waves, of a higher frequency, are needed compared to the carbon atoms in TMS. The frequency absorbed by the nuclei of carbon-13 atoms in TMS is considered to be a reference of 0, and how much the frequencies absorbed by carbon-13 atoms in a sample differ to this 0 reference point is something called chemical shift, with units of ppm. Certain carbon atom environments always have similar chemical shifts, and spectra can be analysed using data tables for chemical shift data. The less electron density there is around the carbon atom's nucleus, the greater the chemical shift. For example, oxygen has a high electronegativity, and if bonded to carbon, pulls electron density away from a carbon atom's nucleus. This is why carbon atoms bonded to oxygen have greater chemical shifts than those bonded to other carbon atoms, and on spectras, absorbances for these carbon atoms are always further to the left on the x-axis, referred to as downfield. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.